Demo from the morning. In the morning and yesterday, we did learn the following. So we learned everything about node process. We learned that it has a single thread V8, which is the synchronous part. We learned that the asynchronous part is libuv. We looked in details yesterday at the event loop. We saw how it has 6 queues. All the asynchronous functions are scheduled here. First queue that it will be processed is the next tick. Second queue would be the microtask queue. And last is the event loop queues. Now, all of that is good. However, we also learned that in case we spend too much time processing any of these functions in V8, it means we are creating a blocking code, which means because V8 is busy, none of the functions from here or here or here is going to be picked up because V8 is busy doing some work. So how do we process basically any CPU intense code? Someone yesterday asked me, what is the definition of CPU intense? How do I identify something intense? Is there a measure? It's up to your hardware, it's up to your application. But I would consider any, for example, mapping a large array would be considered as CPU intense. Doing any kind of encryption, decryption, cryptocurrencies, all of these operations do require a lot of math, CPU intense. So we don't want to process them in the main threads. So what are our options? We have two options. But before I talk in details about the options, let's explore the thread system that's available in any node process. So node by default node process. When you start a node process by running node.exe and then your script, you create everything we saw in the previous chart, queues and all, and the event loop. And that comes with 4 pre-allocated threads. Allocated threads. So what is the meaning of pre-allocated? It means that we don't create the threads, use it, and then destroy the thread. So we don't recreate threads. All threads, when we start node process, are pre-allocated. It means pre-created. All we need to do is to use them. And when we're done, another operation might use them. So think of it as like a taxi. Whenever you want to get a ride, you don't create a taxi and then you make the ride and then you destroy the taxi. A better approach is to have an already created taxi that will take you from to, and then whenever you finish, another passenger will take the same taxi and move to somewhere else. So that's the meaning of having pre-allocated threads. And this way is way faster than creating and destroying threads when you need them. So now we have 4 pre-allocated threads. Good, but how do we use them? We use these threads by using Node API that requires I/O intense operations. So if you have any I/O intense operation from Node API, they are already coded in a way to utilize these 4 pre-allocated threads. Examples: FS. Every single time you write files, automatically the API of read file or write file is going to utilize these pre-allocated threads. Every single time you use crypto, which is a core module in Node, it requires a lot of computation. They are already coded the API to utilize these pre-allocated threads. Another example is whenever every single time you try to use zlib, it requires compression and it is I/O intense operation, then we utilize the threads. Another example is DNS core library. DNS core module also utilize the 4 pre-allocated threads. And we have it as a list in the slides. Where are the slides? Here are the slides. Here they are. So who uses this worker pool? Worker pool is worker threads. In Node, we have 4 of them, pre-allocated. Who's using this for? Some I/O intense modules and some CPU intense module. Every single time you use any API from this module, they are automatically coded to use the 4 pre-allocated threads. Nice. What about if you have something to do that's not from this API? How can we take advantage of, how can we process something blocking that's not DNS, that's not file system or crypto or zlib? In this case, we have 2 solutions. So here's my node process. And it has 4 pre-allocated threads. One option is to create your own worker thread and assign a task for it, which will process in this thread. And once you're done, it sends you out a result and schedule a callback function in the poll queue of the event loop. Okay. So one option, if you as a developer has any blocking code, is to assign this code to an additional worker thread. So you create this thread. You assign a task. When it's finished, it's going to schedule something back in the poll queue. And it's always up to you if you want to destroy it or reutilize that again or again. So that's option number 1. Another option, if we want to process something that is CPU intense, is to create another node process. And this process, we call it child process. And this is a full process that has V8, event loop, and 4 pre-allocated threads and everything. And we can communicate between these 2 processes and send an input, have our blocking code be processed in this child process. When it's done, it's going to send us back some results in a form of callback functions scheduled in the poll queue, So we can pick it up and send a response back or see the result. This way, we avoid processing blocking code inside this main thread of this event loop. So we keep this event loop happy. Others, that's fine. If this V8 is struggling a little bit or blocking something here, that's okay. This process is probably working as a web server. And in this case, it's listening to events on certain port. So it's scheduling request handlers in the pull queue. We don't want to block that. We want to keep them running and assigning tasks. If something needs extra processing, either process it in a worker thread or in the child process. Any questions?
Professor,
Yes.
I have a question. So it means that I I have a question. It means that the system will create a worker thread in initial state.
Yes. Every single time I run node.exe,
Okay,
and then you call script app.js, you create this. And what is this? This is basically just a process that has a thread for V8, a thread for the event loop, and 4 pre-allocated threads. Who uses these? These libraries are using this. Now my question was, what if I want to process something in different than this? So you have some code that's a for loop that requires some processing. You need to do some math to calculate some value for cryptocurrency. So it's not probably a good option to process it here in V8. And making it asynchronous in any way doesn't solve the problem. We know that because it's going to come back and block. We want to keep this V8 completely happy. So what do? We either spin a fifth or sixth or more, something we call worker thread, that is going to process whatever blocking, but that's not a good option. Two good option, I will explain why later. A best option would be to create another node process, we call it child process, and assign this blocking code to be utilized here. Did I answer your question?
so that means the node process will be created once, right?
What's the question?
That the child process will be created once, only one.
Good. Yeah, good question. It's up to you. You can create it once. You can create it and let it process something and destroy it when you're done, or you can create only one and assign to it more tasks as needed. So it's up to you how you want to utilize this child process.
Okay, thank you.
Now,
Yes.
yes.
I have a question that it means that when the V8 is runs and it just creates the new worker thread or the the child process when it runs to the block code. Is it correct?
Say it again.
Yeah, I mean that the worker thread and the child process is just created when the GS engine is run to the code, the block code. Is it correct?
Correct. So we create this worker thread or the child process if we see that we have some code that is going to block this V8. So I'm gonna code an example for you where inside the same process, I have something blocking here. And that's something we should avoid, because if I block this V8, this V8 has working with it an event loop that's responsible to orchestrate my entire application. So blocking this event loop would be bringing your application down for a while until V8 is finished. So we move this blocking code to be processed in worker thread, or we move the blocking code to be processed here in the child process before it sends us back some results. Is that clear?
Yeah, and the next question that does it mean that we only can apply one of these option, or can we combine them together?
You can combine, you can create worker threads here as well if you need in the child process, but yeah, you can combine whatever works best for you.
Yep. Thanks.
But yeah, sure. But your friend was asking previously, or I was like explaining, why do I prefer to process any blocking code in a child process rather than the worker threads? So the first reason is security. So all of these threads inside the process, they share the same memory. While if I have another process, two processes cannot share the same memory space. So maybe for security reason, you really want to avoid having a thread that has access to memory allocations from other threads. So that's first reason. Another reason why I prefer a child process rather than worker thread is responsiveness. What if whatever you're processing in these threads froze? Had something that's caused crash in this process. Crashing your main node process is failing your entire application. While if something crashed here inside this process and you ended up handling this by killing this process, your main app is functioning fine. So you don't get in situations that, oh, now because of I'm handling something that caused the process to fail, now my entire application failed. This is something should be taken seriously. And that's why, for example, in the browser, let's talk about the browser a little bit. In the browser, every single tab you open is a process. And when you open another tab, and this tab is another process. Why they designed the browser this way? For the same reason. One, security. So one tab doesn't get access to another tab's data. And the second reason is responsiveness. So if one tab, for some reason, JavaScript blocked V8 and now it's completely frozen, you can click the X and close it. It doesn't cause the entire browser tabs to freeze and kill the browser. You just kill the tab and other processes are working just fine. So these are the reasons why I'm not going to say the industry, I'm going to say me prefer to use child process rather than worker threads. Also, child process is like probably now 12 years old since the invention of Node. So this is pretty well tested. And this was just introduced 5 years ago to allow developers to give more options for developers to process something blocking. But what we will focus on in this course is how we create and work with child processes. Any question?
Professor, I have a question.
Yes.
So, can we create as many as child process as we need?
As many as you need. Yes, yes, yes. As many
Okay.
as you need. Yeah.
So that time, the OS will kill in a certain point of time if the memory is getting run out.
That depends now on the operating system. If the operating system has limitation in terms of how many child processes you would create, or if the hardware has limitation in size of memory, then yes, this is limitations outside the scope of your application.
Okay. So since a process required the CPU time and also the memory, and usually the OS depends on the priority, OS will kill the process. So is there any way so that we can prioritize that this application process will get high priority before killing it by the OS?
It again?
Is there any way to OS kill the process based on the priority?
Yeah, sure. You can kill the
So
process
based on
or the
its
worker
priority.
thread based on whatever condition that you desire.
Yes. So my question is that is there any way to increase the priority of the? I mean, if I want, I am the five child process, so I want one process to get high priority. Like there is some CPU intensive or a background task is running on that process. So that time I don't want the ways to kill that process. So is there any way so that I can give him the highest priority of that process?
What do you mean highest priority? Higher priority, for example, than the operating system process?
No. So usually OS kill the process based on the priority it has. Like it has the sheet of the priority sheet, and based on that it kill the process, like which is tempo. I mean, I'm not not taking that much
Yeah,
time.
yeah, okay. So in a case like this, you should prioritize which process has which based on conditions that you set.
Okay.
So you can allocate something to process certain tasks, but if you have other limitations, you can kill those and then or pause those until other processes finish before you resume processing something with this. So this is something you have to control,
Okay.
the priority between all your processes.
Oh, all right.
Any other question? Before I show you any code of how we do all of this stuff, I wanted to see something that's really fun to see. And go back to our code. I'm gonna create here a file. I'm gonna call this file threads.js. And inside this file, I'm gonna import crypto. And probably you remember, crypto is one of the libraries that utilize the worker threads, the 4 pre-allocated threads. And when my script starts, I'm gonna measure the timestamp. And I'm gonna call the method ppkdf2, which is a method for hashing using SHA-512 hashing algorithms. And this callback function will be triggered or not triggered. It will be pushed to the poll queue and give me the time after the operation of hashing is finished. So let me test this code if it runs. So I'm going to create another script. I'm going to call it threads, which is going to run nodemon threads.js. So npm run threads. So as you can see, my script finished in 718 milliseconds. That's good. I'm going to have more of these. So 1, 2, 3. As you can see, it's taking now a little bit longer. I'm going to save time and paste the rest. Where I have 20 of the same pvkdf2 doing the same job. I'm going to save. I don't know if you saw that, but what we're seeing is every 4 are processed kinda together. Did you see that? And we see the time, how this 4 kind of quite close in processing time together. So why is that? Why everything is processed in 4s? Well, let's explain that, which is easy to explain. First, when I had one hashing job, the hashing job had one hashing job. The job finished in 700 milliseconds. When I had 2 hashing jobs or 3 hashing jobs, this time increased to about 800 milliseconds. When I had 4, as you can see, it's around 900. And the next 4, when I process 20 now, when I try to process 20, the first 4 finish in 900, the second 4 finish of 900 plus 900, which is 1800. See that? And the next 4 are processed with 220. Well, it's like 600. So every single time, as you can see, we're quite kind of adding 900, and they are processing in 4s. Let's explain simply why is that. And the reason is you have at some point a CPU, and probably you saw it yesterday. The CPU has, my CPU has 16 cores, by the way, 8 physical and 16 logical. Mac OS is seeing 16. Regardless of how many cores, when you have a process that has a lot of threads, the 4 and others, at some point, it's more likely that this process is going to be processed in one core, one CPU core, regardless if I have 4 or 100, right? And since I only have 4 cores, now imagine 4 threads are fighting to run on one CPU. When one thread was fighting on CPU, it finished in 700. But when 3 threads was fighting on a single core CPU, what happened is pause, 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 next, pause, pause, pause. They finish in longer time. When we have 4 fighting on the same core because of concurrency, Remember, they are finishing longer. And now only after these 4 are available again, we allocate the second 4. And after this is finished completely, we allocate the next 4, and so on. And hence we're seeing the results of 900 plus 900 plus another 4, another 4, another 4, and so on. And that's how we explain these results that we saw. Any questions? Now you might be thinking, how about I start node process that has 20 pre-allocated threads? Wouldn't that be like better, having more threads? Well, definitely not. Because now we're gonna end up with a process that will accept 20 jobs and process them in a single core. And I will end up in a scenario where 20 jobs need to be processed in one core. So pause. I need to process part of 20 threads before I continue another 20, before I continue another 20, and they will finish. They will take a really very long time to process. So spinning more IO threads is bad. Having them just enough is very good. So let's do the change. Let's really spin 20 pre-allocated threads before I start the node process. Remember the results. The results were for 4 threads, 900 plus 900 plus 900. So I'm finishing really in allocated time. That looks like this: 900, 1800, 2, 700, 3, 500, 4, 300. Those was the results for 4 pre-allocated threads. Let's spin something with 20 pre-allocated threads, because I have 20 jobs. You might think that's the best thing to do. All right, let's try that. I'm gonna stop this. Let's see. And run this command. As you can see, this command is setting a global variable in Mac OS to set the thread pool, the default pre-allocated threads for the thread pool, to be 20. So I'm having 20 pre-allocated threads. And then next, I'm going to run node to execute this script. Let's run this code, enter. Alrighty, here we go. The results came and everything finished around 2000. Previously, I finished something at 900 and 1800, way before the 2000. So with 20, we delayed 8 hashing jobs to really occur later. Now, this is very, very powerful machine, so probably I could safely make the 4 8, but 20, it's probably just too much, because it really gave me results that were really delayed comparing to the first 8 hashing jobs if I were using 4 pre-allocated threads. How about we try to use less pre-allocated threads? So let's start this with only 2. The results will come as 2, 2, 2 now. But I don't think 2 is a good option, because now we're seeing 700, 2, 1400, This is 4, where previously the 4 were finishing around 900. So yeah, you might argue, but now see the 20. Now the 20 is really delayed a lot. So that's probably not a good option. So they did a lot of benchmarking, and it was decided that the default pre-allocated threads is 4, and that would make Node process capable and functioning well. But if and only if has special requirements, or you are running your application on really different hardware that require some changes to the infrastructure of Node process, you may change that and decide a different pre-allocated thread size, different pre-allocated size, and that would, it is possible. 4, 4, 4, 4, 4, done. So the last one to finish at 4 seconds, I guess that's decent results compared to the other tests that we did. Isn't that fun? It is.
Yes.
Professor, what I can notice that here the total processing time is same, right?
The total processing time, it's not the same.
Is
It's going to
yeah.
always to be different. So here we have 8 seconds with 2, and with 20 we have 2 for the entire 20. It's
And the
different
total
for the
total.
yeah.
I mean, to complete the total job, the whole job, it takes the same time. Like here is 20 job.
To complete the
So
20.
yes,
So to complete the 20, in the case of
since it's
4,
running, yeah.
we finish in 4 seconds. Complete the 20. If we have 4 pre-allocated threads. When we had 20 allocated threads, we finished the total in 2. But we delayed the first 8. The first 8 were really delayed.
Yes. So if
And now
we
with the 2, the total was really bad, 8. So double the size of 4. So I would really, you should find like something that works best, which I find probably the default 4, because the results here are like, these are acceptable and these are also okay, not too bad.
Professor, I mean the average, like the total the time. I mean the total CPU time. If we calculate the total CPU time, it will be same for the all operation and the how many threads it doesn't matter. But for certain thread, like if there is 20 thread, then each thread will wait for like a 2 second, or if there is eight thread, that time first few job will complete within 1 second, and then rest will increase, but total CPU time will be same. So that time total output will not I mean, the job will not complete within a short time if there is much more thread.
I'm not quite following here.
Okay.
So you're saying that
CPU time is same.
is the same?
Yes.
How the CPU time is same? Aren't we seeing different results for number 20?
I mean
Yeah.
for all the 20 job. Suppose for first two, the CPU time is like 1 millisecond, and the second two it's like a 2 millisecond, and third like a third and fourth is 3 millisecond. But total sum is like the 30 millisecond to complete the total job.
No,
I'm
it's
the
not the
20.
same. No, it's not the same for the 20. Why is not the same? So here I have 4, here I have 2, here I have 20 threads.
Yes.
Yeah. So now all of these are going to be processed in one core.
Yes.
So let's say half of this is 1 millisecond. So 1, 1, 2, 3, 4. That will finish in 4 seconds. Okay, let's imagine every half is 1 second.
So we can assume that we have 20 job.
20 job here?
Yes. 20 job here, 20 job. It's not, I mean, it's not,
So we have
it's job
20.
or thread. It's job or
Okay. Let's
thread.
have, we have 20 threads. Oh, I see your point. Okay. Let's break it down. Let's break it down so it's clear for everyone.
Okay. Yeah.
So we have the job is to finish 20. Let's say this is a 20, okay? That's our job. Now the pre-allocated is 2. The pre-allocated is 4. The pre-allocated is all 20. That will make me have 2, 2, 2, 2, 10 times, right?
Yes.
That will process 4, 4, 4, and 5 times. And that will process the entire 20
1 times.
1 time.
Yes.
Now let's say that each one of this line is 2 seconds. So 2 sec, that's 4. 4 times 10, 40 seconds. Now, here we have, oh, it's always going to be the same. Yeah, you're right. It's the total time for processing everything is the same. So 40 seconds, 40 seconds. How is that possible?
Yeah, if you can make
Yeah.
an average, you will see that because there is only one CPU. So
Yeah.
if the
Okay.
first
what I wanted to add to everything we did here, we explained here, is that now this one finished in 40, while this one finished in 1, 2, 3, 2, 5, 4, 8 seconds. And this one finished in 2 seconds. So while the total is still the same, you need to understand that some of them are finishing way faster than 40. Now, for this one to finish, it requires 40 seconds because it's processing all of these and then all of
together.
these, and yeah, together until it reaches
And
back
therefore
and finish that part. Yeah.
yes, and therefore all the thread will get the same priority. But if you compare in the if there is the 5 thread, so first 5 job will complete first, and second 5 job will complete like previous 5 times waiting, and then their execution time. And last 15, I mean the third 15, they will get their execution time and then previous 10 waiting time. So that time, if we make it sum, the aggregation value will be same. Aggregate time will be same, and the average value is the same. If there is a 10 thread or 50 thread or 100 thread, no matter how many threads are there, but their average time will be same.
The thing is, this one we saw finished in 8 seconds. We saw, sorry, yeah, 8. We saw this one is finishing at 4 seconds. And we saw that this one, the last one, finished at, what was the number? This one was 8.
It was the 2 second.
This one was 2. No, this one was 4. This one was, oh, 8. This one was 2.
Yes.
And this one was 4, yeah, and this one was 8.
Yes.
So that's for the last one. So it's arguable that the first one is, yeah.
Okay, we can make a calculation here. Suppose for the two thread only. So first 2 job will complete within 700 millisecond. Okay, and first 1 is 700.
The first one is 700. The last one is, it was 8 seconds. That's
yes.
what we saw in the test.
Yes.
The first one
Yes.
here was 900 milliseconds, and the total was 4. And here what we saw is all of them were processed in 2.
But to complete the, I mean the
So it's
whole
not
job.
quite, yeah, so yeah, the whole job, this is the whole job, number 20. Oh, you mean the average, if you calculate the average of all these numbers?
Yes.
Also,
Yes. All the same. Yeah, you can try.
Okay, I'm not good in math. So if you think that the average is always going to be same, fine.
Yes.
I would agree
I think
on that.
is there anyone can help? I can. I think I don't know whether I'm taking much time. I think okay,
No,
Professor.
it's fine, but we both agree on understand what happened, and we probably both agree that an average number is a good thing. More is might not be a good thing, and less might not be a good thing. It depends.
My point is here that even if we create a much more thread, actually to complete the whole job, it will the total time it will be same.
Okay. What happened here is very special case that I'm running all of these tests on a processor that has 16 cores. I usually run this demo downstairs, which has a processor of 4 cores, really bad machine, and you will see not these numbers. You will see this one is really the worst case. Now here, this one sounds a little bit attractive, but actually it's not attractive. So if probably I make this job at 100 encryption jobs, and then let them fight over 16 cores, that we will probably see some results that, oh my God, really the 4 is giving us a lot of better results before we finish the entire 100. So don't think about it as like just 20 jobs. Think about it as more jobs. Your application is probably receiving requests from thousands of clients. And you need to finish clients as much as in batches as fast as you can. You don't want to process 20 clients together and then the next 20, because all clients are being delayed and delayed and delayed before they can be processed. So you want to start processing in small batches. Just like when you stream a video, you don't send a big chunk and big chunk. You send like small chunk, as little as you could. That's probably the same idea.
Yeah, I got it. So yeah, I am agree on that part because if I have thousands of user and if I have a limited number of thread, so that time some of my client will wait less and some of my client will wait more. So if I have like thousands of thread, so that time all my clients will their waiting time will be same.
Correct.
Yeah, yes, but total time will be same. If there is, I mean, if there is a limited number of thread or how much more thread. If all the thread is processed on a single core, that time the time will be same. And the gross.
Since I'm not good in math and I didn't test that, I would say maybe.
Yes, thank you. No.
So maybe. Any other questions? Okay, let's test something outside this library. So we saw that these people, they really work in using the pre-allocated threads. Now here I'm going to show you an example that not all code in Node uses the pre-allocated threads. And an example for that is, where's that? Oh, here it is. Let's create a file. I'm going to call it, did I create a file? Oh, here it is. Let me call it http test.js. And here I am importing request from HTTPS. I'm doing the same thing. I'm sending a GET request. After I receive the response, I measure how much time it took me to do a round trip between I'm sending a request to google.com until I receive the index.html page. And as you can see, I'm calling this function, I wrapped this code in a function, and I'm calling this function probably 20 times. Am I going to see 4444? Let's test. Oh, node, HTTP test. Nope. All of them, they came around 340 milliseconds. They didn't come in 4444, which really proves to you that not all libraries use the thread pool. Basically, an HTTP request like this one is delegated to the operating system. libuv literally does nothing with HTTP requests. It just requests the operating system to send a request to this domain, and when the response arrives, it schedules this callback function in the pulse queue to come and read the time and print it out for us. So I also find this nice to see. Any question about this? The last thing we should probably do is to learn how we can process something heavy now outside of these four libraries. Let's say we do have something intense that we want to process outside of our node process. So here I'm going to build a web server. You'll find all this code that I'm doing, by the way, in the slides, if you want to test it yourselves. So here I have a function, and this function is calculating the sum of 1 billion. Just keep adding to sum, the I, and returning the value of the entire sum. So as you probably guessed, this is something requires a lot of calculation and it's blocking. So I'm gonna build here a web server. Let me import this first. I'm gonna create a web server and I'm gonna have it listen to a port. And then create a request handler. This request handler is listening for new requests. Once I receive the request, it's going to call the long computation function. After I receive the sum, I'm gonna send it out in response. Let's test this code. So node server.js. I'm supposed to be listening now to a port. So localhost port 3000. It took some time before I received the sum, for sure. Yeah, it is taking a while, and that's for a single request. So what I'm gonna try is to have this in multiple tabs. Probably that's stupid. But you see how each one is like finishing after the other? And now I'm going to click Shift and click all the tabs together, and then refresh all of them at the same time. Look at one finished, now finished, now finished, processing, now finished. Why I cannot, all of them are scheduled in the poll, but Node unable to take them and push them to V8 to calculate the sum, only one at a time. Why? Because each one, when it's pushed, it requires a lot of calculation here. And one more thing I want you to look at is my activity monitor, where I'll kind of try to look for node server. There is node, as you can see. I hope you can see. I'm gonna try to update the frequency, yeah, to be fast frequency, and I'm going to refresh. CPU time jumped to 52%. Not CPU time. CPU performance here, it jumped to 100%, calculating this sum. Why? Well, after the job is finished, is it finished? Not yet. When the job is finished, the last, now the CPU is back to 0. So I'm literally occupying the full capacity of my CPU for and blocking all requests. So the last one really was waiting for the last 9 or 10 before it start processing. So I am blocking V8. So how can I keep everyone is happy and not have all this delay between all of these tabs? So the way we're gonna solve this is the following way. So currently, we have one process. All 9 are scheduled in the poll, but one of them is being processed in V8, finished, and then the next one processed in V8 and finished. So all of these are being blocked. So the event loop unable to push them to be processed. Hence, the last one really is taking a long time to process before it has its turn to calculate the response. So the way I'm going to handle this is the following. Every single time I'm going to receive a request, we are pushing all 10 because we are sending with the refresh all 10 requests at the same time. So all of them are scheduled in the poll. But I'm going to process them all at the same time. How? Every single time I start with one, I'm going to create a process and allocate this job here. Second one, create process and allocate this one here. I'm going to create immediately 9, 10 processes and allocate all these jobs to these processes. So you would assume, you would think probably that, hey, all of them, they will start processing quite at the same time. No one is waiting for the previous one in concurrent way. And this way, now once each one of these finish, they will schedule another call back in the poll just to send the results. And this guy is happy. He's able to receive more and more and more and more requests. But I don't want to keep all of this in memory. So after I'm done with the job, I'm going to kill this one, kill this one, kill this one. So this way, I don't need to spin more and more and more and more. I just spin one, let it process my code, kill it, and then send the response back. This way, we'll see a lot of improvements in the performance of finishing the entire job and a lot of improvement that my main node process CPU use should not exceed high number like 100%, as we saw earlier. So let's do these changes. I'm going to create a file I'm going to call this file compute.js. This is not a file. This is a file. Compute.js. Good. And just to make things easy for everyone, I'm going to have my server and compute back to back. And now I'm going to move the blocking code inside compute. Okay. And now I'm going to remove the calculation inside the request handler. Instead, I'm going to do the following. I'm going to fork the child process. So const child process equal, I'm going to call fork, and then point it out to compute.js. So now the new process will be created, and it is ready to start working from this code. However, I want to send some data here, and I want to send some data here. So how can we exchange data? Very easy, actually. So what we can do is child process dot send. I can send it any data, and I'm going to send a string called start. Let's listen to this data in here. So I'm going to say process, which is the global object process, and listen on the message event. If the event that I receive is start, because I'm sending string start. So if I receive the event that says start, I'm going to calculate the computation. So I can say const sum equal long computation. And after I'm done from computing this complicated thing, I'm going to send it back. So I can say use the same process.send and send back the sum back to the main process. Now the main process should listen to the message. So I'm going to say child process.on message. So if we receive the result, now we're going to send the response back. And certainly that would be a result. What I forget to do is to kill the process. So we can kill any process by calling this.exit. And since there is no error, I can pass the exit code as 0. Now this is kind of complete. Every single time I receive a request, I create a new child process. And I'm going to send it string start. This process is listening for any messages. If the message that we received is a string start, similar to this one, now we're going to compute, send the sum, and kill the process. The main process now is listening on the child for any message. Once we receive the sum that we're sending here, we're going to send it in the response. Let me run the web server. And now test. I still have all the 10 tabs selected, and I'm going to highlight the main node process. So as you can see, I have one process right now, and it is at 0%. Refresh. You see how the one that highlighted is still at 0. It didn't exceed 0. Others are being spin, at 100% killed, and my main is to remain 0, and I managed to process all of them. So our goal is to keep our main node process happy, and we did. The CPU usage did not exceed 1%, while others, let me refresh again, are being created. And if we notice, because it's so fast, I think we did notice in the previous test that some of them are showing 98. Oh, here are two. They're at 98%. So all of the other processes are being really busy calculating all this sum. When they finish, they send the results back. And my main process is still happy. Any questions? That was really fun. Yes.
Professor, I have a question on, sorry, the
Yes.
child process. You are creating a child process using the fork method.
Correct.
So yeah, the child underscore process, it's pointing the newly created child process.
Yes. So this
I have the confusion here.
variable
Yes.
is representing the child process.
And the process dot on the compute.
This is this global object here in this file. So if I use process here,
Yes.
that will indicate the this file process, which is the main process.
Main
And
process server
yeah.
server.js.
Yeah, it means server.js, correct. So process here would indicate server.js. Process here indicates compute.js. And now this variable, when I forked, it represents also compute.js. Because what did I fork? I forked compute.js.
Yeah, okay. Then child process dot on, it also the compute.js.
Correct. So you're listening on the child. So here you see that you're sending to the child this message. The child, this is the child, is listening on the message and receiving the same string. And now the child is sending something. You're sending the main process. Oh, yeah, here you see.
Yeah, it's my question. Since you're sending to on the same process.
Let's change the English description then. You're saying, I want to send a message from this process, and you send this number, and you receive this number here, and that's basically how it's done. It's just like the way that you are I was describing a little bit confusing. I agree.
No, Professor. Your description is very crystal clear to me. But
Good.
it actually the confusing is if it's point the same process. So if the same process, I mean the child process and the process is pointing the same process. So why we need to send? I mean the communicate through the send message, send API.
That's basically how it's done. That's how they coded it. That if you wanna send a message to the child process, you send on the child process. If you wanna send a message from the child process back to the main, use the process instance and call send. Same with on. Here you're listening on events sent from the child process. Here you're listening on events sent from the main process. So if you want to think that this process is main, that's not correct. And I can show you here a little thing. Hey, how about when we start, we console.log process.process ID. Every process has ID, right?
Yes, and child process.id, and if you can print.
Exactly. Yep, yeah. That's what I'm gonna do. And every time I fork a new one,
yes,
I'm also going to print the process ID.
yeah.
And now when I run the
And
server,
please also print the child process.id into the server.js.
oh, here?
Yeah, server.js also please print the process.id, child process.id, child underscore process ID. Yeah.
So we need to identify them now. True.
Yeah.
Still start. So far, we just printed this one, 5.
Okay. Okay.
And
We
5
can make
is a
everything.
process that has 82188. We should see it here. Here it is, 82188. This is the happy one.
Yes.
Now let me send a request. So more processes are being done. And as you can see, 2 and 3 were pointing to the same 9494, which means 2, this one, when we create a new process, this one is pointing to the same, this one. So these are the same.
Yeah. But later we can see the different.
Yeah. So none of these displayed my main process, the happy one, which is 88.
Yes.
88 is just the unique one. But later, we
2 and
always
3.
have 94, 94, 97, 97, 98, 98. So we always see that 2 and 3 pointing to the same PID.
No, sometimes they are different, Professor. Here, if you look at 2 and 3, they're different.
They're not different.
2,
We
3,
have
3.
298, we have 398. We have 397, we have 297. We always have 2 and 3. 2 and 3. Don't mind the order. 2 and 3. They'll always be this identical, which means this one, process.pid, is the same as child process.pid. So this one is reference to the child process. This one is reference to the child process. This one is reference to server. This one is reference to compute, which is the child.
Thank you, Professor. I'm clear. I was confused since same process is communicating.
Yeah, because the way I was explaining it, yeah, it's good.
Yeah, I'm clear. Thank you, Professor.
Any other questions? That's it for today. I really want you guys to master 2 things from today's lecture. The first one is modules. So try to put some logic in a module and call it from your application. It's just fun. We will use them a lot tomorrow anyway, so that's not a big deal. The second thing that I wanted to master is understanding the thread pool, understanding the IO pre-allocated threads. And there is one very important thing I forget to mention. It's in red somewhere. Here it is. That usually we don't like to allocate worker threads or child process for any IO intensive work. We like to allocate child process or worker threads for CPU intensive work. They are so good for CPU intensive work. For IO intensive work, we don't want to allocate child process and worker threads. Why not? Because they're already utilizing the pre-allocated threads. Let these pre-allocated threads do their job. Don't spin new threads or new process to process IO. Spin new worker thread and child process to have some help in CPU intensive work. and not IO intensive work. IO intensive work is already taken care of with the pre-allocated threads. Yes, questions?
Yeah, I found it. I was wondering what's child process, but it's actually another file imported to the meme file. That is the
Yes,
child process.
yeah, so child process is basically a new process, completely new process, as you saw in the activity monitor. So this is going to be this server JS is going to run inside a process that has V8, event loop, and 4 pre-allocated threads. And when I call fork here, what actually I'm doing is I'm creating another process with V8 and 4 pre-allocated threads and event pool to run compute. When you say fork compute, you're creating a new process. And when I'm sending, I'm doing send and on, send and on. All I'm doing is I'm exchanging data between these two processes.
Okay.
Does that?
Why
Yeah.
we imported that child process in line 2, and we are
This function fork is
Mhm.
not a global function. This function fork is a function that comes from a core module that comes with Node called child process. So I just imported this function before I use it. That's why. Because this function is not global. This function exists in a package or a module called child process. So I needed to import that before I can use it.
Okay.
Same word create server here. Create server is not a global. It's a method that comes from HTTP. So I needed to import this function before I can call it. Same idea. Clear?
Okay. Thank you.
You're welcome. Any other questions?
Professor, I have a question.
Yes.
We, because you in the previous example, crypto, because crypto is supported by the is module, right? Right.
Yes.
But that means we use the worker thread. So can we convert it to using child thread process?
Very good question. Very good question. So here, previously, we had something called threads, I guess. Yeah, it is. And inside this file threads, we imported crypto and we had some work. Your question is, can I do this in a child process or worker threads? The answer is no. Because worker threads and child process, they will not help much with IO intensive work. So let the worker threads, the pre-allocated ones, take care of them. Don't like reinvent the wheel. So that's also a line copied literally from the documentation. I copied it as is. That you should only use them for your own CPU intensive work. Don't use them for these. These all Node API is taken care of. Don't think that, oh, I'm gonna use DNS or file system or crypto in different child process. No, don't worry. Use it in your main process. The pre-allocated threads will take care of that. They are not going to block. They are calculated in their own threads. It's taken care of. It's never going to block your event loop. Okay?
Okay, but the one more question. The one more question is the so in the latest example, can we use the worker thread to calculate to run the computation?
In my example, I didn't use worker threads. No, I used
Child
process
Yeah.
instead. Yes. Yeah, I use child process instead. The code for worker threads is not something required for this course. But anyway, I can I can show it like a quick example. So the way you do it is you create a new worker and you send it some inputs, and you start on the worker to listen for any outputs. And now inside the worker, basically you do the same. You get all the data from worker data, you process it, and you send it back to the main worker. And if inside your app you decide to kill this variable, basically you destroy your worker threads. So it's up to you how you put it and do it. So, but the code for this is not something I want you to practice, or you can find it in the documentation.
Okay, thank you, sir.
Welcome. Any other questions? I think everybody's waiting for the moment